Okay, so we begin our look at the calculus. And the first main part of calculus is looking at the slope of a curve. So quite often students are shocked to find out that calculus is just about slope. Little rise over run. But there is a big catch. You can see the graph in front of you here at the point 2 and 4. I want the slope of that curve. And typically when you're calculating slope, you use 2 points. But the catch with calculus is we want to find the slope of that curve at a single point. So before we try to deal with that, we got lots of things to consider first. I think we'll just zoom in because there's one thing that's really important. I understand about calculus is that once we zoom in on a curve, you can see at that point 2 and 4, it starts to not really look like a curve anymore. It looks like a straight line, and we call that local linearity, which basically means exactly what I'm showing you here. If you zoom in on a curve, it eventually starts to look like a straight line. So to measure the steepness of that curve, or the slope of that curve at that point 2 and 4, we have to create something called a tangent line. And you'll see that that tangent line just touches that curve in exactly that one point. That so-called point of tangency is what it's referred to. And again, if I zoom in, you will see that that tangent slope mimics the curvature of that line, or I should say the linearity of that line exactly at that point 2 and 4. So that doesn't solve our problem that we have to calculate the slope of this tangent line, which of course represents the slope of the curve at 2 and 4, but the catch is we can only use 1 point. So how the heck are we going to do that? Well, let's shut our tangent slope off and let's just go back to basics here. Our basics are going to be, we're going to look at a pair of points on this curve. Now, incidentally, I'm sure you've recognized our friend here. This is the basic quadratic, of course. And it shouldn't be no problem to find the slope between a pair of points. So we can find the slope between 3 and 9 and 2 and 4. Now, that's not a tangent slope. That's referred to as a secant slope. So there's two types of lines we'll be dealing with in the early stages of calculus. The secant line, and that's connecting 2 points on a curve, and eventually we'll deal with that tangent line, which involves just a single point on the curve. Okay, so let's do some written work and make sure we're clear on what we're going to try to find. I'm looking at my quadratic function y equals x squared, and I'm interested in getting the slope of this curve at 2 and 4. So the slope of the curve. And that's the weird one. That's the one that's we're going to use create a tangent line to mimic that slope of the curve. And why I say that's the weird one, that involves a single point. So when you're looking for the slope of a curve, you are looking for the tangent line, which will, of course, mimic and measure that slope of the curve. So before we do that, let's do our more familiar situation. We're just going to calculate the slope. And since we've got a couple of lines happening here, let's make sure I label this one as the slope of the secant. And we're going to use our slope formula, of course, which will be rise over run. And there's nothing weird about this calculation because that'll involve a couple of points, 2 points. And 1 point will be, of course, our point of tangency, that 2 and 4. Which I guess I can rewrite here, our point 2 and 4. And maybe we'll call that x1 and y1, because that is our focus. And our second point, well, we got lots of points to choose on our quadratic, but I think I said earlier there, we'll go with 3 and 9 on our quadratic. And you're probably asking yourself, well, what is this secant line going to do for me? Well, it's going to give you a pretty rough approximation of the slope of the curve at exactly 2 and 4. And we'll go back to Desmos there in a few more seconds and illustrate that a little more clearly. So if we find the slope of the secant between 2 and 4 and not really a nearby point, but it's not terribly far away at the point 3 and 9, we can get a steepness that'll hopefully be somewhat the same as the slope of the curve at exactly 2 and 4. So we go y2 minus y1. Of course, that's going to be 9 minus 4. On the top, that's our rise, and our run is going to be 3 minus 2. So the slope of our secant looks like it's going to be 5 over 1 of course, 5. So we'll just box that, and we're far from done. So let's have a look at Desmos and see how close that secant line is coming to matching the slope of our tangent line. Okay, so here we are. There's our secant line graphed on Desmos for us, and I'm mainly just concerned about the slope of that line for now. And you can see, even if we zoom in, it's not doing too bad of a job. Of course, around 2 and 4. But of course, it's not exactly what we need either, but it's a good start. So if I put on our tangent line again, we can see that there's not a whole lot of difference between the slopes of those two lines. And if we zoom in, we'll see it's not that bad. So our grade 10 calculation there, that secant slope, is doing at least something to help us determine what the slope of the curve is at exactly 2 and 4. So the next step is going to be, well, how can we get a better approximation of our tangent slope? Well, if I drag this point, I can drag this point even closer. And this is where calculus comes in. The closer I can drag these 2 points together, you can see the better approximation we're getting for that tangent slope. Now the catch is I can't drag them completely together because of course my line just disappears there, as you can see, because that's going to be a strange rise and run of both 0. And you've seen that previously when we're dealing with some rational functions, that it is possible to get 0 over 0. And guess what? That's what you're going to have when your secant line coincides, or the 2 points in your secant line coincide together at the single point of tangency. So let's just do one other calculation. Maybe we'll just take 2.5. I don't think I'll get that to stick there exactly, and it looks like I did. If we put 2.5 into our function and square it, we'll get 6.25, and then we'll use that as our second approximation of our tangent slope. Okay, so take 2, our second secant slope. I'll just use a different color just so you know we're calculating 2 different secant slopes. And I guess we'll write out our original point of tangency again. That's going to be 2 and 4. And that's our x1 and our y1. And what I said a few moments ago there, we're going to use 2.5, and then square that to get 6.25. We'll just use decimals. It's a little less threatening. And there's our second point. And then we can just do our good old rise over run calculation where we go y2, 6.25. There we go. 6.25 minus 4 divided by 2.5 minus 2. And then we'll get what? We'll get 2.25 divided by 0.5. So if I double the top and bottom of this fraction, we can get rid of the decimals. So if I times the bottom by, I guess down here, times 0.5 by 2, we'll get 1. And if I double the top, we'll get 4.5. So it looks like our next approximation here. And for now, let's just call it a secant slope before we move towards our tangent again. It looks like this secant slope has a slope that's 4.5. So that would tell us that our tangent slope is probably closer to 4.5 than it is 5. And I thought we might as well just go back and look at it again, and you can see that's getting pretty close. And even when we zoom in around that point of tangency, there's still some discrepancy there that we want to get rid of, but for intents and purposes of what we're trying to do, we have a pretty decent approximation of our tangent slope, or the slope of that curve, at 2.4. It's roughly 4.5 right now. And again, how can we get a better approximation? We get those points even closer and closer and closer together. So I could go like 2.1, and I could put 4.41 in there, which I think I will actually do, and we'll go for round 3 of a secant slope, and this will get us an even closer approximation to the true tangent slope. Okay, so here we are back in our written work. We're going to look at our 2 points now, and we still have our point of tangency, of course, at 2 and 4. And then we'll use our second point even closer at 2.1. And remember, when we square that, of course, in this quadratic function, we'll get 4.41. So we do our rise over run, and we'll get 4.41 minus 4, the difference in our y's. That's our rise. And then the difference in our run is 2.1 minus 2. So So you can see that our rise and run are getting smaller and smaller and smaller. So right now, what is our run? It's 0.1, of course. It's the difference between those two x values. And it looks like we got 0.41 on the top. So if we do what we did last time, try to get rid of the decimal on the bottom. We'll multiply the bottom by 10 to get rid of that 0.1. That'll give us 1. And times the top by 10, we'll have 4.1. And without a calculator, we've just determined that our slope of our secant line for these pair of points is 4.1. So now we can be, I guess, a little more confident to say our tangent slope is probably close to 4.1, closer than it was, closer than 5 and closer than 4.5. So we can do this another 6 or 7 or 8 times, and that would be probably hard to endure. But I think you get the idea that our secant slopes will eventually, not eventually completely mimic our tangent slope, but can do a pretty good job of estimating what your tangent slope actually is.